In this lesson, we discuss model selection. We will start with a motivational example about the receiver operating characteristic ROC curve, how to construct an ROC curve to compare different classifiers, and finally, we will discuss how underfitting and overfitting play out as the model gets more and more complex. When evaluating machine learning models, we need a method to compare different classifiers or even different configurations of the same classifier. The ROC curve helps with visualizing a classifier's performance across different decision thresholds. Let's take a step back and give you a motivational example. Consider this logistic regression classifier. In logistic regression, we need to define a threshold or a cutoff to classify an example as positive or negative. So in this very example, suppose we picked 0.05 and we ended up with this confusion matrix. So we were able to classify 3 positive examples and 3 negative examples, but we also ended up with 1 false positive and 1 false negative. Let's tweak the classifier a little bit and suppose that this classifier is going to be used for medical diagnosis application. Then it's important to get high specificity. So I will set up the threshold as 0.1 so I can get all the true positive correctly, which are the 4, but this is going to be at the expense of the false positives. So now I have more false positives. And let's add one more scenario. So if this application is about spam detection, so I would like to have 0 false positive. And as you can see here, this is going to come at the expense of the false negative. At this point, I have 3 classifiers with 3 configurations that I need to compare their performance. To construct an ROC curve for the logistic regression example, each confusion matrix is going to present a single point in this ROC plot. And as you can see, the x-axis represents the false positive rate and the y-axis represents the true positive rate. And the way we make sense of this curve, a classifier with a perfect accuracy would be on coordinates 0, 1, which means 100% true positive rate and 0% false positive rate. And the diagonal line represents a random classifier. Now, suppose that we used our confusion matrices for different models and different configurations to construct these curves. So let's say one curve is a decision tree, another one for logistic tree, another one for linear regression. So now, depending on the problem and depending on the trade-offs, which is more important, is it a spam problem or a medical diagnosis problem, we try to identify the classifiers and their configurations that maximizes our goal, which is the true positive rate or the false positive rate. The area under the curve, or AUC, quantifies the overall performance. Suppose that AUC equals to 1, this means this is a perfect classifier. And if AUC is 0.5, this is a random classifier. So the higher AUC indicates this is a better model. Finally, we wrap up this lesson with a plot that illustrates a well-known problem. So as the model becomes more and more complex, it risks overfitting by memorizing the dataset. And this is something that we really want to avoid. And this is a classical view of model complexity generalization. So modern perspectives have evolved over time, but the key idea is the same. So essentially, the model initially is going to underfit, and as we improve its complexity, it starts to reach some inflection point where we go from underfitting to overfitting. In summary, we discussed ROC curve, area under the curve, and overfitting along with model complexity.